Okay, so we are in the very last question for Chapter 11 of Statistical Rethinking, second edition. So it's 11H6 is the question. And so this has three parts, so we'll look at them separately. But we're looking at a data set called Primates 301, which is part of the Rethinking package. Oh, and by the way, if you're going to run this code, you need to make sure that you've gone through these first several cells here to in order to install and load the Rethinking package, as well as scan the well, kind of the gears of the Rethinking package. So anyway, let me find where we're at here. Okay, so we're looking at that data set, and basically we're trying to understand how the brain size of a bunch of different primate species is associated with social learning. Okay. So in the first part here, we are, well, let's just load the data first. So I'm loading the data and I'm calling it D, and this is what the data looks like right here. Just run this again. So we have the genus and species name of the animal, and then genus and species. Okay, so all together separately. And then we have a bunch of other things here that I don't really know what subspecies is referring to. I don't know what, well, these look like just ID numbers assigned to each of the species. Research effort is, we'll use that. So this is, I guess, maybe how many studies are conducted on or were found for each of these, or something analogous to how much effort has gone into researching these animals. And then I think that we will also look at, I think, just brain here, and that refers to brain size. So, okay. So right away we notice that there's some values here. Like right away we see that there's an NA value here for this particular species. And in the future we will learn how to deal with missing values, but for right now we don't know how to do that. And so we're just going to filter our data to get rid of any NA values, and specifically values of NA for one of the variables that we'll use, brain, which is brain size, research effort, or social learning. Okay. So I'm making a new data set here called D2, and I'm just filtering D that has the complete cases of the particular variables that we're interested in. Okay. And later, we'll learn that we're going to convert research effort to log of research effort, and brain size to log of brain size, and for reasons that I'll explain, I'm standardizing that one right there. Okay. So first one is we want to model social learning for each species as a function of log brain size. Okay, and we're going to do that with a Poisson distribution. Okay, so we're modeling social learning as a Poisson distribution, regressing it on brain size here. Okay, so here's our model right here. Okay, so here you see social learning. It's distributed as a Poisson model with parameter lambda, and then the log of lambda, so its length function being the log function, is given here. Okay, and so we go through this. I had to go through and redo this to make sure that I'm using log-like, because this will be handy later. So we want the log likelihood. This will help us do something later that you'll see. So I've already ran this, so we're supposed to interpret the resulting posterior. And so here's our posterior. Now, roughly what it says is that that brain size is positively associated with social learning. Okay. Now, remember we have standardized brain size, and that will allow us to compare species more easily. So this is saying then that 2.8 standard deviations in log brain size is one standard deviation in log brain size is associated with log of 2.8 social learning. Okay, so anyway, So I don't have a sense of how realistic any of that is, but if I look at what the so anyway, so that translates to 16.4 social learning. I don't have any sense of whether or not that makes much sense, and so what I'm going to do, so to see if that is a value that makes any sense, I'm just gonna, as a rough estimation or a rough assessment here, I'm going to look at what the average of social learning is, and it's 3.1. So this is saying that a relatively small increase in brain size is having a very big effect, apparently, on social learning, and that seems a little bit weird to me. So so we can kind of we were introduced to a function that is very helpful earlier in this chapter, and it's called post check. Okay, and so what post check allows us to do is it plots all of the data in these bluish dots here. Let's zoom in on this. Okay, so the actual data is in these bluish dots. The estimate is given in a hollow dot, and then I think that we have, I think it's like the 89 and 90, the 89% credibility intervals with that line, and then I think that the pluses are like the 99% credibility, yeah, something like that. I can't remember exactly, but anyway, so it's helping us to see what our posterior prediction, what our posterior predictions are compared to the actual data. And you see, for a lot of these, it does fine, but then there's several outliers where the data is, well, the data is far outside of what the model is expecting. Okay, so so what this suggests is that there's things that we are not understanding then about our data set that should go into our model of social learning. Okay, so now in the next part, we're given what one of those variables might be, and that's research effort. Okay, and so we're going to do the same thing, but we're going to add research effort as one of the predictor variables, right? So we have the same model. I'm calling this one MB, model B, and it's the same model, except for now we also have a term for research effort here. Okay, so so we go through, and then we're asked to interpret the posterior and how the models differ from one another. So that's what we're going to do. So I've ran all of this already, and here you see the two posteriors, or the two summary of the posteriors here. And then the first model, we saw that brain size had a coefficient of 2.8, and now it's still positive, but it's drastically reduced. And we see that research effort is very, it's positively associated then with social learning. And this seems weird because, well, why would how much we research something affect social learning? Probably it's the other way around. Probably things that are intelligent, primates that are intelligent, we spend more effort researching them, or something to that effect, or they lend themselves to research, or who knows. But anyway, so we can also look at the post check for both of these, and we can see, like, for instance, that some of these kind of outline points are being better approximated by the second model here, right? So for instance, this high up data point, its prediction is somewhere, it's one of these, and now it's getting closer. But this is kind of a terrible view of on what, which predict, this is a terrible view to compare prediction by prediction. So instead what we'll do is we'll try to identify these outlying points with PSIS, okay? And then look for the high K values. Remember, a high K value coming out of the PSIS is telling us something, is identifying data points for which our model is not predicting very well, okay? So, so that will kind of help us compare these two models a little bit. So, so here I have the PSIS scores point-wise for both models. It is for this reason that we have to use the log-like function in our models, right? Because without the log likelihood, we can't calculate PSIS or WAIC, okay? And then I am identifying suspicious points, which is which I'm calling K values between 0.5 and 1, okay? And outlier points, or what I'm calling outlier points, which are are data points for which the k-value is greater than or equal to 1. Okay, and so so I'm going to plot these here. All right. So along the x-axis, I have the PSIS scores for the first model, and then the y-axis is PSIS scores for the second model. And this diagonal line here represents that the PSIS scores are equivalent for the two models, right? Now, so what that means then is that models that are, I'm sorry, data points that are below this line means that they have a worse fit for MA. In other words, MB, the second model, would do a better job of predicting them. Okay. Now the outlier points are color coded in red, and the suspicious points, are merely suspicious points are in orange here. Okay, and so what we see is that, with the exception of the one suspicious point, all of the outlying points are doing worse in model A. Okay, so so now the question is why. Why is there this relationship with research effort? And so I suspect that in this case, it's because, remember at the very beginning, we filtered our data based on complete cases. Okay, so oh, that's a weird thing to say. So I suspect then that what is happening is that the more highly researched species are less likely to have incomplete cases. In other words, missing data, and therefore more likely to be included in our data set, right? And so what we're getting then is this apparent effect of research effort, right? So all of this now asks us to draw a DAG that may explain the results of our model and our data, okay? And so I've drawn the DAG here. Okay, so we have brain size is affecting social learning, and that brain size may also be affecting research efforts. Okay, and research efforts is affecting data filtering, and data filtering is affecting social learning as given in our truncated data set here. So I think that this is maybe explaining what is happening with the predictions in our model. Now, it could be that this arrow right here from brain size to research effort is non-existent. It may be that the animals that we have that are more highly researched are highly researched for reasons outside of brain size. But I don't know enough about this stuff to know. But so even if this arrow wasn't here, given the results of our model, if it was just the line from BS to SL and RE to DF to SL, that might also explain our data. And so we'd have to go through and run more models to see if there was associations between BS and RE and so on and so forth. Okay. So anyway, we'll call that good. That is the end of this chapter. And then next we are on to chapter 12, which is monsters and mixtures.